Alright, so let's try this new system to record the classes, to record the classes. So let's get started. So this is thermodynamics or ES305, and let's say this will be lecture 1. And what is today? January 16, 18. All right. And this will be chapter 1. Introductory concepts and definitions. So basically this is a little bit of, not review, but giving more detailed information to the stuff we're discussing in the first day of classes, which was like a brief summary of what would be the material covered throughout the semester. Alright, so obviously the important part when you take a class is to understand at least what is the class about. So this class is thermodynamics. Okay? And we said the other day, if you had to summarize your class, or if you had to summarize what you did in physics about dynamics, you can just use one equation. What would be that equation? Summation of forces equals to ma. All right? And then for thermo is related to what? To heat, which generally the symbol used for heat is the letter Q. Okay, so if we just look at the word thermodynamics, what could be a definition of what needs to be covered in thermodynamics? Let's say you have no idea, but you read the title. What would be your guess? Go ahead.
Motion caused by heating.
Okay, motion caused by heating. That would be a good guess. But again, in this class, like I mentioned, we don't really care about how the heat is transferred, but that's a good one.
The way heat affects a force.
Okay, basically to make it easier will be the relation, if you want, between the heat and dynamical systems, no? Okay, really the definition is because we can rewrite this equation here under the form of work and energy, which you will see, okay? If you remember, what is the principle of work and energy? Is change in work is equal to the change in kinetic energy, all right? So really, the more detailed definition for thermodynamics is the relation of heat with the other forms of energy derived from the dynamic equation given by summation of forces equals to ma. Okay, so let's write something like that. So thermodynamics is, let's say, the science that studies the relations between heat Q and the other forms of energy derived from the, let me just say, dynamic equation, summation of forces equals to ma. All right, so the other day we also started to see or try to understand how to use the new vocabulary for thermodynamics. So basically, I gave the example of water, which is a substance. You can find it in two different states, no? States will be like liquid, solid, or vapor, okay? How do you define the state of a substance? And we say that the state of the substance will be defined by its what? By its properties, because the properties of liquid water is not the same as the properties of solid water. I think the best example is the one that when you put a full bottle of water, liquid water, into the freezer, what's going to happen? It expands. That means because property density is not the same anymore, no? Even though you have the same substance. Okay? All right? So we need to define that vocabulary. So let's maybe start by property. So what's a property? What could be a property? I just put this one, but I agree. A state of a substance is defined by its properties. Okay? But a property, if somebody asks you, what is a property? It's like a physical characteristics of something, no? Okay? So let's just write something in that direction. So it is a measurable physical quantity such as, I don't know, we can say density, viscosity, and there is all other kinds, okay? So when I do this, I'm going to add a couple more things before we go to what is a substance. So basically, a property is a physical characteristics that can be measured, okay? So this is our first page. Okay, so when you look at a property, we can have two different kinds of properties. Some are called extensive, some are called intensive. Okay, so the difference between extensive and intensive. It doesn't matter if you fully remember what is an extensive or an intensive. What's important is that you realize that there are two different kinds of properties. For example, let's say you want to evaluate what is the total mass in this classroom. So property, mass. How would you find the total mass in this classroom? Maybe you go around, you add the weight of what? All the chairs, your weight, all the tables, your backpack, whatever is inside the classroom, you add it up together, all right? And that will be the total mass of which is within the system classroom, okay? Now, so mass is a property. What about if somebody asks you, what is the temperature in the classroom? Do you take the same approach? Do you go and ask what is your body temperature of each one of you and you add it up together and that will be the total temperature of the system classroom? No. So the other one, temperature, is like a global property, no? Okay? It's not the summation of each one of them. So you see those two properties are defined differently. Okay? So one is called extensive, the other one is called intensive. So the extensive is the one like the mass, where you need to add all the different parts in order to find the total value of the property. Okay? The intensive property is the one that is not the summation of all the different parts, but it's like a global property. All right? Depends on the surrounding. So let's just write down that very quick. So let's see, extensive. Okay, I try to give very simple definitions. So, what do we say about extensive? Extensive depends. Okay, so depends on the amount of parts. Okay, let's say. Within the system. And we say one example. Could be what? Mass of a system is equal to the summation of all masses within the system. Is that more or less what we said? Okay, I don't try to give anything complicated, okay? The important part here is not the definitions, it's the concepts, the idea behind. And the intensive what do we say? Okay, so it's not extensive. So basically, you can say it is. Let's make it very simple. It is a global property. We can just say it is uniform within the system. And we can use as an example what? The temperature, no? I mean, since I put a comma, what could be another one? What about, yeah, the pressure, no? What about pressure? Same thing. Okay, and the pressure, these other ones. Okay, so basically so far we just started by definition. We said what is a property? It's a physical, is a measurable physical characteristics or quantity, all right? And then we said you have two different types of property, extensive and intensive. So we went a little bit off track here. Really the next thing I wanted to put after property was what? Substance. So why is substance? I mean, anything we want to deal with, no? Is what could be a substance? A substance. Yes.
Any collection of matter?
Okay, I like that definition. Okay. So a substance is any collection of matter and now that we know what a substance is, how do we know? So we have property. How do you know what is the state of a substance? Remember, you just said before. How do you know if the water is liquid, solid, or gas? So what is it? The state of a substance is defined by what? Its properties. Okay, let's see what other definitions can we put. I mean, this is just for you to get familiar with the vocabulary. If you want, the semantics we'll be using during the class. So 3, the other one I can think of is process. Okay, in addition to that, guys, let me know if you have any problem in reading the class notes on the monitor, okay? Because this is like a little bit of an experiment, so you need me to do it bigger. If you want me to write maybe every other line instead of every line, I don't mind doing those things, okay? It's for you, so it's not really for me. It's for you to make things clear. All right, so what's a process? For example, when you go from liquid water to solid water, you need to go through a process. Okay, so that will be, if you want the definition, we're gonna say is when you go from one state to the other. But again, one state doesn't mean that it needs to be from solid to, let's say, liquid. Okay, or from liquid to gas. You can go from, let's say, cold water to hot water. No. Okay, it's still a process. If you want to heat up water, it's still a process. All right. So let's say what's a process is the action of going from, oops, should I do that in blue, from one state to another. So basically, let's say state 1, this is the process, and you go to state 2. Any questions so far? All right. So since we're talking about processes, I think the other day I gave 3 or 4 new terms. One was called adiabatic. The other one was what? Isobaric. And the other one, isochoric. Okay, so what was the meaning of, let's start by the middle one. What is isobaric means? So a process that happens at constant pressure. What about isochoric? That happens at constant volume. And adiabatic, no heat. So basically you could say that Q is equal to 0, or delta Q is equal to 0. Is this recording or no? Okay, I guess it's recording. Now I have a question, I have a doubt, because I'm using this program here. No, I think it's recording. I'm using this one to record, but I'm using this program to capture whatever I'm writing. Okay. I think I'm doing the stuff correctly. All right. We'll find out at the end of the class anyway. All right, so 3, we have state, the processes, which are, we can be adiabatic, isobaric, or isochoric. Yep.
Sorry. We also do isothermal. No change in temperature? Or
Yes, but the thermal would be the adiabatic,
okay.
when Q equal to 0. Okay? All right, so now, the other thing we need to define is that system. Okay, so basically we have 2 different types of system. Now this is the part where I wish you had fluids before, because it makes it easier, but if it's not the case, it's not the case. All right, so you can have, remember we kind of mentioned that in thermodynamics we're going to study how the heat is being transferred, okay, and we mentioned conduction, convection, and radiation. Okay, but I kind of also told you that that's not the main part for this class. In this class, we don't care about how the heat is transferred. We just care about what's the consequence of having transferred that amount of heat. So for example, if you're going to boil water, what is important for us is that the water is going from the liquid state to the liquid gas, no? We don't care that much about how you provide the heat to the water. All right? What's important for us is to study what is the amount of heat, for example, you need to boil the water. How you apply it, we're going to do a little bit, but it's not the important part for this class. Okay? So when we talk about conduction, convection, radiation, or anything in thermodynamics, you need to define a system. Okay? Before being able to apply the equations, you need to define the system. In statics, you have your system that was whatever was the solid, no? And you apply the equation to that solid. So basically, in thermodynamics, you need to do the same thing. So we have, in this case, we have, if you want, two different kind of systems. One, I mean, it's not exactly that, but just for the explanation, let's say you study conduction. We say conduction, you need a solid medium, no? Okay, so your system could be your solid, all right? Your solid with a surrounding, okay? What about convection? What was the difference between conduction and convection? Convection, we said that this time it relates something about a medium that is moving, no? Like a flow, all right? So this time, if you have something that is moving and there is a flow, what does that mean? In other words, it means that there is a flow. The mass is still constant, but it will be mass going inside your system, and it will be mass coming out of your system. All right? So if we do this, if you want, we'll have closed systems, and we'll have what I'm going to call here open systems. Really, in textbooks, they are called control volume systems. Okay, so to give in very quick definitions. Closed system. All right, let me just do a couple of pictures here, and then I'll put a definition under. So if you have an enclosed container, and I do in dash the system, this will be a closed system, no? All right? The amount of matter inside the closed system is constant. Okay, the other case of closed system we deal a lot in this class is like a piston cylinder assembly. So again, the mass within the system will be constant, but the volume might change, no? Okay? So again, I'm not trying to give complicated definition, it's just simple stuff. So what could be a definition, a very simple definition for a closed system? So a system where the mass is what? Is constant. Okay? So basically you will see, like, I will say half of the class is really on closed system, and the other half will be in what? Open systems. Even this semester, I think I might change the order of my class notes. I might do closed system and then just study open systems. I don't know, we'll see, because then it might create a problem with me in order to give you homeworks, no, out of the textbook. All right, so open systems. So open systems, all right, let's say will be so in here I do the system, and now what's going to happen is that you're going to have substance going in and substance going out within your system, no? Yeah? And this is the type of system you study all the times in fluid, because in order for that to happen, what do you need to have? A fluid system that goes through the systems, no? Yeah, like a flow. Let's say you want to cool something. Let's say this metal, this is a engine block, and you want to cool it. So what you need to do, you need to put water inside the engine. It will be some coming in, some coming out, no? Okay, and in the meantime, the water will absorb heat from the engine, correct? All right, but it will be a flow, okay? So in this case, open system, just to let you know, is the same as what they call in most textbook control volume. Okay, why do you think they call it control volume? On the other one, we had constant mass. In this case, what is constant? The volume through which the flow is going through, no? Okay, but since you use closed system for one, why don't you call the other one just open system, no? Instead of control volume, okay? All right, so a definition for this one, what could be a definition then for open system? What could be a simple definition? Whatever you want to tell me. Okay, a system with, let's say, flowing mass. Is that okay? I mean, try to keep it simple, okay? Okay, any questions so far? Yes.
In an open system, does mass still?
Yes. I mean, the mass within the system is going to remain constant as well. But what happens is that it's always going to be like new mass, if you want. So it's still the flow of mass. Yeah.
So we won't deal with like an air compressor where it's taking in air?
Yeah, so for example, what I'm saying here, you will say the amount of mass going inside the system will always be equal to the amount of mass leaving the system. It will not be a change in mass within the system in this class. Okay? All right, so 1, 2, 3. Four. Okay, here I'm going to answer a question so that you know that is if we don't use the table, the other solution is a lot worse. Okay, so something that we have to do in this class is to use tables in order to solve problems. Okay, it's not to make things more complicated, it's actually to make things easier. Okay, and without going into too much detail, I'm just going to show you now why we are using tables, and if we were not using tables, what would be the solution? And then you tell me which one you want to do, okay? All right, so let's put over here. Why do we use tables in thermodynamics? Okay, so believe it or not, you already know a lot about thermodynamics. Then you got this one, I don't know, from chemistry or physics. But what is this relation over here? What is that relation? Ideal gas. So it says ideal gas relation. Okay? So, all right, so what is the ideal gas relation? What information can you get from the ideal gas relation? So let's see. What is P? What is V? And what are T? What are there? What do we say about, you remember, like an intensive property will be the pressure, no? And the temperature. So pressure, volume, temperature will be what? Properties. So that's not bad, no? Because we say that something that we're going to be doing all the time in this class is what? To see, we're going to define a substance by the state of its properties, no? So in order to be able to define the state of the properties, it's good that we have one equation that already gives us the relation between three properties. All right? Okay? So let me just rewrite this one a little bit differently because it's easier for the math. All right? So do I need to say that P is pressure, that where V there is volume, and T is temperature? Let me do it this one here for one. So P is pressure. V, I do this V that way to differentiate with all the V's. This is volume. T is temperature. What is R bar? Gas constant. That one, do you remember I told you to print one page with the units? I think that one should be in there. If it's not in there, you can add it. Okay? And then the last one is N. What is N? Number of moles. So number of moles of what? For the given substance, no? Yeah? All right, so let's just rewrite this a little bit differently. So let's see, how can we do that? So, all right. Let us rewrite the ideal gas relation. Okay, so we have PV equal nRT. So by definition, what is N? How do you find the number of moles? What is it? Okay, but what would be the other way without looking at that relation? Number of moles is the mass divided by the molar mass, no? So mass divided by molar mass. So then that relation here becomes what? PV equals to mass over molar mass R bar times T. Or we can rewrite this as P V divided by M times R bar divided by M times T or this is the way you will find this equation written in thermodynamics textbooks. PV equals RT where what would be letter V? Okay, but should be V over M, which is called the specific volume. Who says specific volume? Why did you say specific volume? How do you know that?
Because it's an intensive property, it's variable mass.
Okay, so basically in thermodynamics, when you use the term specific, what does it mean?
It's a variable mass.
Basically is per unit mass. Okay, so that's what I'm saying, if you knew it. So specific volume. So for example, you're also gonna have, instead of, generally you will see, we'll use capital letters, okay, for or uppercase letters for the full property volume and lowercase for specific values, okay? But we can mention that later. And in this case, what will it be? R will be R bar divided by M. And what would that be? This is still called also the specific gas constant, but this time this R will be related to what? To a specific gas, no? So let's say air, nitrogen, or whatever. So specific gas constant. Okay, I do this because it's easier to work with PV equal RT than with PV equal nRT, okay? I don't have that N over there. So this is still the ideal gas relation. Okay. Trying to think about what time we are done. We still have half an hour, no? 12:30? Because I'm not good with that, so stop me, okay? So page 5. Okay, so the important part over here, let's just recall that equation. PV equal RT. This is our ideal gas relation. All right? So what's important here to know is that all these threes, again, are properties so this relation is always going to give us what? The value of one property in function of two other properties, no? So if P, we want to know P will be RT over V. If we want to find what will be, let's say, the volume, what will be the volume equal to R T over P. And if we want to find T, what will be T? 1 over R P times V. Okay? So here, which are our properties? This is a property, 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 this is a property. So what's the conclusion? Each property let's say, what do you want me to say? Depends or is in function of other two properties. Each property is in function of two other properties. Okay, so that's a problem. So far, when you go to mathematics and you study those functions in, I guess it's in calculus, generally you know the functions that you have is in function of how many variables? One, no? You have whatever, f of x, and if you want to know how is that function f varying in function of x, what do? You take the derivative. That's a function of the derivative. When you take a derivative of a function, is to see how that function is going to vary with respect to the variable you use to take the derivative. Okay? So df dx means what? How is the function f varies in function of x. Alright? Okay, but now what happened is that each one of these properties are in function of two other properties. So how do you do? Yep. You need to take partial derivatives. Okay? So do you want me to do a general mathematical example, or you want me to use the relation PV equal RT? PV equal RT? Okay. So let's say we have, so using the ideal gas relation, so let's say I give you, so let's use the first one, okay? Using the ideal gas relation, let's just use the first one. P equal R T over V, okay? So we have the P depends on which two variables? Which two properties? T and V, no? Okay? So that means that if we take the derivative of dP, that will be equal to what? You say partial derivative. So if we take partial derivatives, what does that mean? So we're first gonna have the R over there that is bothering. So we're first gonna do what? We can take first, let's say, the partial derivative of what? Of P. We can first vary in function of T, no? Yeah? Partial T. But when we do that, what do we need to do? We need to keep V constant. That's what a partial derivative is, no? Okay, after we do that, now what can we do? And this will be now dt. Yeah. Now, what can we do? We can take the partial derivative of P with respect to what? V, and this time what will be constant? P become constant, and this will be here dV. Okay, so what is the mean of this term? I mean, I'm not asking anything complicated. Is partial derivative of P of the pressure with respect to temperature, okay, to T, comma, keeping the specific volume keeping V constant. Okay? That's why you need partial derivatives. Okay. This one, if we kind of say the same thing, what would be this one? Partial derivative of P with respect to volume V, keeping P constant. Keeping T, what did I do here? Oh, V,
Keeping P constant.
what did I write? I mean, this is a run, not keeping P constant.
Taking the pressure with respect.
Okay. This one with partial derivative of P with respect to T, keeping V constant. This one will be partial derivative of P with respect to V, keeping keeping T constant. You're right, so I did it wrong in both places. T and T. Yeah, you're right. So this is T over here. Okay, so in order to make it a bit shorter than what I could go, what type of equation is this? It's a partial differential equation, no? So in other words, if we wanted to if we want to know the value of one property in function of the other two properties for a certain, let's say, constant volume or constant temperature, we'll need to solve the partial differential equation, no? Okay. So what do you think the tables are? The tables are the solution to those differential equations. So what do you rather do? Use the tables with the solutions to the differential equations or solve the differential equations? I guess use the tables, no? Okay? So you see, using the table is not fun, but it's a lot less tedious than having to solve differential equations. Okay? Alright? So I'm not going to go, but generally if you say, you know, this differential equation is exact, this is equal to, or is equal to a constant, it's equal to 0, because if equal to 0, what does that mean? That P is constant, no? Alright? So something I'm going to do, though, is that, alright, so keep that equation in mind over there. Instead of going into more details about how to derive the solution, I think it's better to give you a conceptual idea. So now I don't want to destroy this. Let me check if I can go here. All right. So I hope this is still recording whatever is on the screen. So the other day, okay, course material, didn't put classes below. I just told you this is important right here, okay, those two things. So please print this one and bring it to you in class, And then this one over here, we don't need it yet, but you're soon going to need it. We have here those kind of two figures, okay? So let me just do both of them. So, very simplify. First one, we have T. Yeah, but I need to copy it first. Okay, I know them. Okay, no, I know them. So it's up, Okay, I know how to do this. So it will be up and the one will be down. Okay, so we have this, where this will be, okay, I'm not going to go in detail now, okay? I'll just tell you. But if you want, this will be a curve that will tell you what is the state of a substance. So on the left-hand side of this curve will be liquid. On the right-hand side of this curve over here will be gas, and whatever is in between will be a mixture. So for example, when you go from liquid water into gas water, you boil it, you don't have liquid water, and then magically within a split of a second you get everything becomes gas. No, it's progressive. As you heat the water, some of the water become gas, some of the water still remain liquid. No, okay, so in here will be the mixture in between. All right, so something important here, you see we can vary T and V. If we vary T and V, what do we need to keep constant? Pressure. So this equation here, this figure here, gives you the values of T and V for different values of P constant. So basically, this figure over here is some type of solution to these differential equations, no? Yeah? We take the partial derivative in function of this property with respect to T, this one with respect to V, but we still need to keep one of them constant. So this will be the first figure I show you, and the other one we have is the PV diagram, where this time you kind of have the same thing over here. But this time, if you have P and V, what do you need to keep constant? The temperature. Let's say T1 constant. Okay, so if you want, this would be some type of graphical solution to partial differential equation, which was defined by this one. So this is a partial differential equation to be solved. Okay, so this one, so this will be the graphical interpretations. So in other words, tables give the solutions to the partial differential equations. So again, conclusion, what is better? Use tables, no? If we don't use the table, what is the alternative? Solve the differential equation. And actually, I'm going to be honest with you, I've never done it, but man, I can do it. But I think the difficult part is not to solve the differential equation, is to know what is the initial condition of your boundary of your PDE, okay? Because if you don't know the initial conditions of your substance, you're not going to be able to solve the end condition. Okay. All right. So we have this. So some definitions. We define that. What else can we do? Let's see what I have here. This is some old class notes. How much time we have? 15 minutes. We'll probably finish with that. So let's read over here specific. The term specific means in function of mass. Or means per unit mass, or in function of mass. So basically we had V equals volume over this, which is specific volume. Okay. Obviously you cannot have something called specific pressure. It makes no sense at all, but okay, let's say you have delta Ke, which will be changing kinetic energy. You can have delta Ke will be specific kinetic energy. Okay, and you're gonna have a lot of specific. Okay, and I just say generally specific we use, so specific values or specific properties use lowercase. Okay, that's the way it's in the textbooks. Okay, the last thing we're going to do is just to look at the temperature. Okay, so let's say this will be let's start by Celsius. So then Celsius is connected to Kelvin. Then what we have Fahrenheit. How do you spell Fahrenheit? F-A-H-R-E-N or R-E-N? That's what we have Google. Is it that way? Yeah. 5. Yeah, okay. It's an N and then Oh no, I put the H at the wrong place. Damn, I did it's 2H. Alright, so you see, Google is good, huh? Fahrenheit, and this will be, so the last one should be what? Rankine. Okay, so let's say we're going to use at the boiling temperature. We're going to look at the icing. And that would be the other one would be the absolute zero. So for Celsius, quite easy. What would we have? 100, 0, and minus 273. Okay, I'll round it off. Okay, I don't care. I'm not that picky. So now, if we use Kelvin, what is the absolute zero in Kelvin? So just get reversed. So this is 0. So then the 0 becomes what? 273. And the 100, 373. Okay, so basically from here we can get the relation that the temperature in Kelvin is temperature in Celsius plus 273, no? All right, let us do the same thing for the Fahrenheit. So what would be the boiling temperature in Fahrenheit? 212. What would it be then the one of icing? Pure water, we said the 0 or 0 Fahrenheit coincides with what? The 0 degree Fahrenheit is the freezing temperature of seawater or salt water, no? Okay, that was the difference. And what would be the absolute 0 for the Fahrenheit? Minus is 459 for something, but let's say 460. So now, what would that be in Rankine? Would that be this one? 32 plus 460? 492, no? Same thing as before. And this one will be what? Plus 212 plus 460, 672. So the relation between Rankine's and Fahrenheit is what? Temperature in Fahrenheit plus 460. And now comes the difficult one. What is the relation of Fahrenheit with Celsius? 1.8 times the temperature in Celsius plus 32. Okay guys, so this will be the end for today. We only have 5 minutes. So next time we start the derivation for the first principle of thermodynamics, probably for closed systems. So let me stop this, see if we did record it. Done.